Welcome to our business track from the Data Science Salon YouTube channel. For this session, we have Anupama, Joshi, Director of AI Engineering at Target. Companies are moving towards AI and machine learning very, very fast, and data scientists are building models and training models every day. But challenges arise when models are deployed into production. How do we maintain multiple models? Creating a common platform that allows model management and deployment easily and reliably is becoming a necessity for organizations to accelerate product development. Anupama shares the challenges faced and the solutions used to make this process much easier. Enjoy.
So I'm Anupama Joshi. I'm managing data science, data engineering teams at Target for personalization and some of the platform building things. And I faced a lot of problems which was discussed in the previous presentation. And some part of this presentation will talk about how to provide infrastructure for data scientists so that they don't get bogged down by 100 different things and quit. Though at the next company, they probably will face the same thing, but at least they won't leave my company. So that's all. Okay, so that's why the topic is challenges in machine learning for model building to deployment. Okay, let me go to the next slide, which is a nice slide. So we use machine learning. Everybody wants to use machine learning. We are trying to change, personalize everything, recommendations. We use it at different places. So I worked before at social media, a genomic data analytics company, some other companies where, everywhere we are trying to use machine learning. Now at Target, we are trying to personalize everything. So if I log in, I'll see like, oh, your favorite items are this. And, yes, I like, because I keep drinking coffee and then Coke to get working on certain type of things. So the customer experience is evolving and everybody needs personalized recommendations, and the data scientists are building these great models. But what do they really want to do? What makes them happy, right? They want to get the clean data. They want to write this awesome machine learning code, preferably once, not too many times, train it once and then deploy. But they don't want to deal with the deployment. There are 100 different issues with deployment. Writing that machine learning code, figuring out what next to do, and that's what's going to make them happy and productive. But in reality, they do way more than that. They try to figure out data, they run SQL queries, they clean out data, they do feature extraction. Then they, try to see what is their model doing, the performance analysis, progress management tool, how to serve the model, how to scale the model, how to monitor model. So actually writing the machine learning code becomes a very, very tiny part of their day job. And, again, I think, that kind of like, puts limitation into what they can envision and what they can produce. Because, if you're trying to put agile framework into machine model development, then this process is very, very weird, and they can't really, put this up into a format. And so for 6 months, they generally can't produce anything. And, again, as we saw in the previous presentation, people say that, what is your data science team doing? They're not producing anything. On top of it, not only that, they have to deal with different tools. Like, there are new tools coming up every day. There are open source tools. There are some companies will use some legacy tools. They have to learn that and deal with all of those things. So what do we do? What do we do at Target? So this is a typical machine learning life cycle, right? We do ingest data, transform, model training, model storage, management, model deployment, blah, 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 blah. So in this talk, I'm going to focus on the first two boxes, which are the feature engineering. I don't find my cursor. And then the last two boxes, which is serve layer, the model storage management and deployment part. And because, once we have the first thing figured out, we'll train the model, and there's a lot goes on in the training of the model, figure out the model. That's a topic on its own. So I'm going to focus on these two aspects of things. Okay. So feature engineering. Without feature engineering, there is no model. Your models depend on how good your features are. So, but what are the challenges in this feature engineering? We need a labeled data set for training, retraining. We need to, figure out everybody has a varied feature definition. What I am considering as, say, an income range for certain demographic is not the same as somebody else is saying as an income range for demographic. I mean, I'm just giving, a vague example. So varied definition across the team. Suppose two people are building the same model which is using the same data, the feature definition will be different. Features are not being reused because, people not often talk to each other, but also, they don't know that other person is using the same feature. It's hard to serve up-to-date features because the data is constantly changing. There's inconsistency between training and serving because at training time you are using different code, and then at serving time you probably are using a different mechanism. Maybe the machines are different. There's some floating point arithmetic difference. You don't know what's going on here. So the solution which we are trying to figure out is basically unified feature storage, to how to store all these features in a standardized format, and so that people can discover them and people can reuse them, right? So the goal of the unified feature storage is basically easily discover and reuse features, access these features for training, and the same features for serving. And then that gives a consistency between training and serving, and gives also the standardization of features. So within Target, basically there are inventory-related data, storage-related data, sales, promos, or item-related data, and all of these data gets used across the models to predict what the users are going to use, or some kind of assortment optimization, which one of the talk which we saw. So so when we are storing all these features together, basically, it's trying to create a centralized platform where you can discover these features at one go. So it's basically creating a directory of features that any team can see what is the definition. It guarantees the data quality, so you'll run the same type of validation across the teams. We'll have a standard feature format which will have a metadata, so which will create a registry or directory of feature where somebody can actually build a UI and then search for the features. Hey, do I have item attribute features in this feature store? Particularly when the inventory is constantly changing, certain type of features searching becomes a very easy to very efficient to be utilized. Also, it becomes a centralized platform to standardize the definition of storage and access of features. And for serving time also, in the real-time serving particularly, this comes very handy that you're using the same nuances and nomenclature to get the feature, and there's no difference. So a brief architectural overview for this. So the feature store service is in the middle, and then the services and data lakes from which it gets the data. There's the feature engineering part, and it can also have ad hoc files. And all of these will stream to a Kafka stream, which will actually feed to two different data stores. One is an offline data store, which is used for training, and one for more of the real-time scoring thing. And the models and services will use that. A little bit of a detailed view of this is basically we have all this data in our system, and then we do the feature engineering. There are multiple feature groups. There's features, and then there are metadata, and the models are looking at all of that together. So that gives, across the company, it gives an access to everybody for all of these features. So this is not a this is very simplified view. This work is constantly ongoing, and it's a constant challenge because people are always the tendency of everybody is to write a small quick workflow and a script and to build the model and try to make sure that things are put in production. But putting it in a structured way actually in the long term benefits the organization as a whole. People leave the code what they have worked on is non-interpretable for the next people who are joining. So having all these storage helps whoever is going to work on the next. Plus, it's just a knowledge base of everything. So again, back to my diagram of machine learning lifecycle, that was the part where we focused on the feature engineering. We built our model is trained. Now what? Now what do we want to do? So we want to serve this model, right? So there are multiple challenges again in the servlet. Like, we need to do model management. So what does that mean? That what was the metadata for this model? What was the version of this model? Are you updating it? Are you changing it? Is this the model? I'm trying to put it in production. Who is going to use this model? What are the so on the website, what type of placements are going to use this model as a strategy for those placements? So what are the runtime requirements for this model to run? What are the hyperparameter tuning? Again, I think you're probably all familiar with all these terms. Then I want to deploy this model with the dependency management, zero downtime. I want a fallback mechanism. Suppose I'm trying to upgrade this model and then it's not getting some problem. I need to fall back to the previous version. I need monitoring and alerting who is using. I need to maintain my SLAs. Everything, all the problems are getting dealt in servlet. So we are devising a platform called ML Serve platform. I mean, these names are very generic, but again. What is the Serve platform doing? It's making it easy for scientists and engineers to manage and deploy machine learning models. It's building platform. Basically, the goal is to shorten the time to production so that people are not sitting in silo for 6 months and then coming out with the models. By that time, the requirements have changed. Something is different. Some teams are going and talking to external vendors. So we want to shorten the time to production. We want to drive standardization so that everybody tries to deploy the models in the similar way. Everybody is not trying to reinvent the wheel because, across, we have on-prem clusters, we have, OpenStack, we have some GCP. How do we standardize all the deployments? So we want a general framework which standardizes all the storing and managing and packaging, deploying, which is agnostic to algorithm. It's a simple collaborative filtering algorithm or a deep neural net. We want to deploy it in the same way. Data, how much data it is, what type of programming language people are writing in R or Python or Scala or Java. We want to have the similar type of deployment serving platform. Processing mode, deployment location, as I mentioned, we have multiple platforms. We have internal cloud, we have OpenStack, GCP, and people want to run their models on local environment to test out. So we want to have a consistent layer. So the Serve platform basically focuses on a model DB and the deploy layer. So in the model DB, we store the versions, the environment, core representation of the model. This is more used as a repository of models so that company like Target, where there are multiple people trying to solve similar type of problems, sometimes across the organization, there is a less amount of communication, cross-geographic, because of the cross-geographicness, time differences. People want to know, I want to solve this problem. Has somebody else in the company has solved this problem using some model? So this also serves as a repository of models where people can say, somebody is using a collaborative filtering model for personalized recommendation. So they will go and figure out what is this model and try to see what this model's recommendations are doing, and if they want to use it. Hence the model storage and stores the entire model in a different way. Also, the models are written in R, Python, Java, as I said. We have different REST and gRPC interfaces to connect to the model DB service. And then what it does is basically it has bindings for all those languages, and it stores all the metadata and all the information in model DB, and which is getting used in the scoring layer. So for example, if you're writing a R model or R code for your model, you are going to include a library called model DB in your code, and then you're going to write the predict function, get your model from the DB, get your data, transform, and create the output and scoring. And the dependencies are like, say, for example, this particular is a forecasting model, so which uses different dependencies. So basically, it provides all the dependencies for that particular model. And then it gets packaged and Dockerized into a standardized format. So the package model deployment from model DB, it goes to the packaging utility, which takes the inference logic and the configuration and then packages it into a Docker image. So it's basically the server management of, which kind of gets it all together and deploys it using the deployment utility. So that kind of standardizes the whole pattern of what you want to take the model from the training pipelines from the model DB into the deployment utility and deploying across the platform. So the images are built combining the information from the model DB about all the data, and then the packaging utility is taking the inference logic and then deploying on the server. So it also takes care of whether you want what's your typical usage is going to be, whether you want a load balancer. The model developer doesn't have to worry about any of these patterns. So in general, the server platform uses different language binding. It has logging and monitoring. So models are obviously trained using in the training pipeline. You use the data, and all the configuration and customization is provided. And then on top of it, the scorer model is going to score multiple models. Then there might be compositions and aggregations. You might have basically an ensemble of model where your output is basically dependent on output of multiple models. So it will call all these, get the input and call all the models and aggregate the scores, and then the aggregation model will aggregate it to serve into the output service layer. So this is all an automated process. All the users, data scientists have to write their predict models and their score models, and then the rest of the architecture is taken into consideration. The model DB also has a very dynamic nature. Depending on what type of models you have, you can actually configure different databases. So if you want to store your models in data in say GCP buckets, you can just give a path for those models, or you can, if you just want to store coefficients, you have small models, you can store in Postgres or Cassandra, and then at the loading time it will get loaded into the memory and get scored. So there's a lot of optimization allowed and provided for the users to play around with their models and model sizes, but which is transparent for them so that they don't have to deal with the nitty-gritties of that. Okay, so basically that covers the unified feature store and the server platform, which are the main pain points before the model training and after the model training. I mean, model training, I think is another base. Again, as I said, this talk is just about these two things. So that's what I want to present. So.
Thanks. So we have a couple questions. First from Liang Wu, how do you make the unified feature service robust? I imagine the unified feature pipelines can be broken by any engineer, data scientist wrong code challenges or some failed upstream tasks.
Yeah, so basically when we try to locate the feature, try to register the feature in a feature store, the job in which the feature is getting computed is also part of the metadata where the feature is getting stored. So if the job fails, first of all, the feature doesn't get updated into the feature store, and it stores the email. So the way the monitoring and alerting, particularly for the failed job for feature engineering happens, that kind of controls that people can't check in wrong code and which is failing code into the pipeline. So that's one way of that. And every username is also associated with the feature. So, you can track down to the person who is writing that feature so that he can fix the problems. So that's, one way of fixing that. Also code reviews and, other stream of typical software engineering practices is another way.
Great, thanks. We also have a question. This one got a thumbs up. It's from JJ. Does your new ML server platform support reinforcement learning models? If so, could you talk about the unique servering layer challenges and solutions experience to support reinforcement model deployments versus traditional model approaches?
Not yet. I mean, we don't have a reinforcement learning model in production using the platform yet. There are more deep learning models, for computer vision models and some standardized model, but not reinforcement learning models. Maybe soon.
Is that something you're thinking about adding, or do you have ideas about that?
Yeah, once the models get into production, they'll probably flow to the same platform. But right now, we are still exploring more in reinforcement learning in general, so not yet.
Okay, thanks. Well, thank you again to Anupama.
Yeah, thank you.
That was a presentation by Anupama, Joshi, Director of AI Engineering at Target. Anupama shared the challenges and solutions used to make the process of making a common platform that allows model management and deployment easy and reliable. If you enjoyed this presentation, please make sure to subscribe to our channel below.